Hello. So welcome to this next video in our exploration of Lagrange's theorem. So exploration. This is exploration of Lagrange's theorem, and this is part 12 of it. Part 12 of our exploration of Lagrange's theorem, and so far we've seen what Lagrange's theorem does. We've just said, look, if G is finite and H is a subgroup of a finite group G, then the order of H must divide the order of G. This is what Lagrange's theorem is telling us. So what consequences were we able to derive from Lagrange's theorem? Were we able to say that if G is finite and little g is an element of big G, that the order of little g divides the order of big G? Right. Is this true? Right? And is it a consequence of Lagrange's theorem? And what else did we find out? Did we discover that if if the order of G is some prime, then G can actually be generated by any non-identity element. Here little g is some element of G, and little g does not equal to the identity element. Did we say that if a group is prime, if the order of a group is prime, then that group is cyclic? Right? That is, did we say that the group G can be written as G to the 0, G to the 1, G to the 2, all the way up till G to the P minus 1? Alright. Now, in the previous video, we were exploring something a little different. So, what we're exploring was the idea that, well, suppose we have some group and the order of G is some prime power, p to the alpha, right? Here p is prime and alpha is being taken to be at least 1. Alpha is greater than or equal to 1. Does that imply necessarily that there exists some subgroup h of G such that the order of H equals to p? Right. So if the group has order p to the alpha, does that mean that there's a subgroup of G that has order p? Right? That's what we're trying to find out. And this begs the question, well, how do we prove that a group has a subgroup of a given order? Right? In general, how do we do that? If we had some group, what? Let's call M. We had some group capital M. And we had, how can we determine if the group capital M has a subgroup N of some order? How do we determine that? And so is it sufficient to just pick an element of H, an element of G that has the order G? For instance, suppose we found little g, right? Suppose we found little g element of G such that order of little g equals to p. Would that be enough for us to conclude that there is an element, there is a subgroup of H, subgroup of G that has order p? That is, would the set H equals to G to the 0, G to the 1, all the way up till G to the P minus 1, would that set be a subgroup? Would H be a subgroup of G? Right? And if H is actually a subgroup of G, have we now found a subgroup of order H whose order equals to P? Right? If we're able to write H in this form, right? So suppose that if indeed finding an element of order P is enough to give us a subgroup of order P, how else can we restate this theorem or this claim that we're making? Right? So can we now restate it as follows, that if the order of a given group is some prime power, right, would it be enough to show that this implies that there exists some little g in G such that the order of G equals to P. Right? Would this be enough? Is there another way to show that there exists an element of a group that has a given order? Right. So if finding an element of order P guarantees us a subgroup of order P, isn't it just sufficient to show that if a group has order P to the alpha, then there must be an element of order P? Alright? If this is sufficient, can we prove this claim? That indeed having a group of order P to the alpha guarantees us an element of order P, right? How would we prove this statement here? Or what possible tactics would help us? Right? What techniques would help us? Well, I mean, let's study just having order G equals to P to the alpha, right? So suppose we have order G equals to P to the alpha, all right? Well, we don't know what the subgroup is, but let's say let's let's suppose that H actually has some subgroups. What possible orders can the subgroups have? What are the possible orders of the subgroups, right? I mean, what does Lagrange's theorem tell us? Does it tell us that, well, first of all, is the order of G, is G finite? If the order of G is P to the some prime power, is a prime to some P to the alpha, can we conclude that G is finite? If G is finite and H is a subgroup of G, what does Lagrange's theorem tell us? Does it tell us that the order of H must divide the order of G? But if the order of G is P to the alpha, what are the possible values that order of H can have? Right? Is it true that order of H could be 1, or maybe P, or maybe P to the 2, or maybe P to the 3, all the way up till maybe P to the alpha? Is that right? Does 1 divide P to the alpha? Does P divide P to the alpha? Does P to the 2 divide P to the alpha? Do all these elements up to P to the alpha divide P to the alpha? Right. So is this an exhaustive list right here? 1, P, P squared, P3 up to P to the alpha. Is this an exhaustive list of what the possible orders of H can be? Okay. So given this information, how can we prove that, given this information that we've learned, if Lagrange's theorem is telling us that, well, the order of any subgroup could be 1p, p squared, p raised to any power less than alpha, well, how can that information help us to somehow guarantee that there'll be some element of order p, right? Or that there is a subgroup of order p, right? How do we guarantee this? Well, what do you think? Okay. What about this strategy instead? Suppose we're able to prove that if the order of a group, well, let's suppose that alpha equals to p, alpha equals to 1, then don't we know that, or let's say this instead. Suppose we're able to prove that if the order of a group, if, suppose we're able to prove that, sure, if the order of G is actually P to the alpha, then there exists some subgroup, right? So, such that the order of that subgroup, right, actually equals to P to the theta, where theta is less than alpha, right? Suppose we're able to prove this. Would that be helpful to us? Well, isn't this always true given that H I mean, the identity group is a subgroup of, the identity is a subgroup of any group. So, I mean, can't we write the order of, if this, let's call this group I, can't we write the order of I as just p to the 0, which is 1, right? So isn't this always true that just, well, if we got any subgroup, right, there must be a subgroup of order p to the theta where theta is less than alpha. Isn't this always true, right? Given that the identity, the set of just the identity is a subgroup of every group, okay? So we can't, are we saying that we know that this is always true? All right. Is there any way we can restrict this statement a bit and maybe say, well, okay, is it then true that if order of g equals to p to the alpha, can we say that the order of h equals to p to the theta, or let's say p to the omega, where omega is less than alpha and less than or equal to 1, right? Can we prove this instead? Right? That is, what are we saying here? That, look, if a group has a power p to the alpha, right? Are we saying that, I mean, can we determine that there must be some subgroup whose order is p raised to some non-zero power, but that's less than p to the alpha? That is, for instance, in this case, if these are the only options, the order of h can be 1, p squared, p cubed, up to p to the alpha, can we guarantee that there must be some subgroup h whose order is less than, that is not p to the alpha, that is one of these options less than? Maybe p to the alpha minus 1, maybe p to the alpha minus 2, certainly also not the identity, but something from p to p to the alpha minus 1. Can we guarantee this? Suppose we're able to prove this fact. Suppose we're able to prove that, look, actually, for any group of order p to the alpha, for any group of order p to the alpha, there is some subgroup, right? So suppose we're able to prove that if order of g equals to p to the alpha, right, then this implies that there exists a subgroup h of g such that order of h equals to p, or p to the 1, or p to the 2, or one of these, let's say up till p to the alpha minus 1, right? So suppose we're able to prove that this is true, right? If this is always true, that for any group, suppose we're able to prove that for any group, it's indeed true that the order of the group is always, that there's always a subgroup whose, such that the order is some power of p that's less than alpha, right? And not 0, of course. So suppose we're able to prove this. Would this be enough to show our proof? Would this be enough for us to conclude that indeed for any group of order p to the alpha, it's necessarily true that there exists a subgroup h of g such that the order of h is actually equal to p, right? Is this enough? Is this enough? Is this enough? Is this enough to? Is the above statement that there's always there's always a subgroup of some power of p less than alpha enough for us to conclude that there must be a subgroup of order p, right? What do you think? How can we use this statement, the first statement, that there must exist h such that order of h is less than alpha? How do you think we can use that to show that there must exist a subgroup of order p? Well, could an example help us? Let's suppose that the order of g is actually, let's say, p to the 7, right? No, let's say some prime p raised to the power of 5. Let's say that's our group, right? P to the 5. Let's say p to the 6, right? Well, if the first theorem is true, that this implies that there exists a subgroup H, right, of H, there exists a subgroup H of G such that order of H equals to p to the theta, where theta is less than between 1 and less than or equal to 1 and definitely less than 5. Suppose you could guarantee this. Well, I mean, well, suppose this is always true, then that means that order of H, what power must it be? What are the possibilities for the power of H? Well, I mean, can it be 5 if theta has to be less than 5? Well, let's put it this way. Suppose we actually found that H such that order of H equals to p to the theta and theta is less than 5 and greater than or equal to 1. Well, can theta be 5? Okay, if theta can't be 5, what are the possible values of theta? Can we say that the possible values of theta are 1, 2, 3, and 4? Okay, well, what happens if theta equals to 1? Well, if theta equals to 1, aren't we just saying that we found an H such that order of H equals to P? Right. And isn't that enough? Wouldn't we be done then? Wouldn't we have shown that at least for when the order of G equals to P to the 5, P to the 6, right? This was 6, okay. So then it's going to be less than 6, okay. So suppose we found that actually the subgroup H that we picked, whose theta power is less than 6 and greater than or equal to 1, the theta is actually equal to 1. Wouldn't we be done? Wouldn't we have found a subgroup of G that has order P? Alright? So what other powers could H be? Well, I mean, could it be 2? Could it be P to the 2, P to the 3, P to the 4? Well, what if maybe the problem was actually notorious and we found that the order of H, this was 6, that the order of H actually turns out to be P to the 6. Alright? Question. Is a subgroup of H also a subgroup of G? Let's think about it. Suppose H is a subgroup of G and we found some L subgroup of H. Is L also a subgroup of G? Right? If a subgroup of H is also a subgroup of G, well, now aren't we saying that the order of H is also some prime raised to some, okay, this is P to the 5, sorry. P to the 5, P to the 6 we said was not allowed. So suppose order of H is actually P to the 5, 1 less than P to the 6, say. Okay, well, this theorem is telling us that there must exist some subgroup of H, right? Isn't it telling us that there must exist some subgroup of H such that the order of that subgroup is P raised to some power that's less than 5? Okay, well, so we're being told that there exists some L. So there exists some L subgroup of H, right, such that order of L equals to P to the theta, where theta is less than 5 and greater than or equal to 1. Okay, well, what possible values could order of L take? Well, could order of L be, let's say, P to the 4? Is that possible? If order of L is P to the 4, and our theorem is guaranteeing us that there must be, right, isn't L, if L is a subgroup of H, doesn't that mean that L is also a group? And if the order of L is P to the 4, aren't we also guaranteed then that there exists some M subgroup of L such that order of M equals to, let's say, P to some power less than 4, maybe P to the 3. Right? And so question, is it clear now why, if we can prove that for a given group G, right, for a given group G, there exists, right, if we can prove that for a given group G, whose order is P to the theta, sorry, whose order is P to the alpha, if we can prove that this implies that there exists, right, if we can prove that this implies that there exists some H subgroup of G such that, well, order of H equals to P to the theta, where theta is less than alpha and greater than or equal to 1. If we can prove this, does it make sense why that would be enough to conclude that there must be a subgroup of G whose order is actually, there must be some subgroup S of G such that the order of S equals to P, right? Does it make sense why? I mean, given that this reduction makes sense, that is, if we can find, let's say, if having a group of order P to the alpha guarantees us a subgroup of order P to the alpha, say P to the alpha minus 1, of at most P to the alpha minus 1, and let's say having a subgroup of order P to the alpha minus 1 guarantees us a subgroup L of, let's say, order P to the alpha minus 2, right? And having a subgroup of order P to the alpha minus 2 guarantees us a subgroup of order P to the alpha minus 3, right? Will this process end? Will we reach a point where, well, if we keep reducing the powers, will we reach a point where we have a power, the only possible power is P to the 1? So maybe, let's say, we arrive to some, let's say, K, subgroup K, whose order is P to the 1, right? But if H is a subgroup of G and L is a subgroup of H and so on and so forth, and K is a subgroup of whatever came before it, doesn't that mean that K is a subgroup of G? So then, haven't we found a subgroup of G? Haven't we found a subgroup of G such that order of K equals to P, right? Wouldn't this be a proof of our theorem, right? So if you buy this idea that showing that the order of G is P to the alpha implies that there is some subgroup of order P to the theta where theta is less than alpha, if you buy that this idea, right, is going to guarantee us that there is a subgroup of order P, what's the next question? What question does this raise? Does the question now become, how can we prove that order of G equals to P to the alpha implies that there exists H subgroup of G such that the order of H equals to P to the theta where theta is less than alpha and in between 1 and definitely less than alpha, right? How can we prove this statement is the question. Right. So now it appears we have two strategies. One is this. Another strategy we could use is maybe find, okay, well, show that there exists some little g element of G such that order of little g equals to order of little g equals to P, right? That was the other story. We said, well, if we can show that there exists an element of order P, maybe we can show there's a subgroup of G whose order is P. And the above one is also seems to be suggesting that if you can show that there's always a power less, then maybe we also guarantee that there's a subgroup of order H. So which method are we going to use? Which one is better for us to use, right? Well, let's see. Suppose we consider the first tactic first, just the one before, the first tactic, that there must exist some subgroup whose order is P to the theta, and theta less than alpha. Okay. Well, we don't know that this is true, so can we prove that this is true? Right? Can we prove that it's always true? What would it take to prove that the order of H actually equals to P to the theta? Right? There's some H whose order is P to the theta. Right? Well, let's put it this way. Suppose order of G equals to P to the alpha. Okay? But there is no H, doesn't exist any H subgroup of G such that order of H equals to P to the theta where P to the theta is some power less than alpha. Where theta is some power less than alpha. Okay, let's not be sloppy. Let's write this down well. Suppose that such a H actually doesn't exist. What does that mean? Suppose there is no subgroup such that the power P to such that its order is P to the theta and theta is between 1 and alpha. What does that mean? Would it mean that for all H, right, for all subgroups here, H being non-identity, would it mean that for all non-identity subgroups H of G, right, order of H is definitely equal to P to the alpha? that all subgroups are equal to p to the alpha, right? All right. Would that be true? If we're saying that, look, if the order of G is p to the alpha and there doesn't exist any subgroup of order p to the theta where theta is less than alpha, right? And if we also, does that then mean that for every subgroup that's not the identity, right? Because what's the order of the identity? Well, the order of the identity is what? Is it 1? Otherwise known as p to the theta, right? P to the 0, sorry. Okay. Well, but if we're focusing on theta between 1 and alpha, right? So does it make sense to consider the case where the subgroup is the identity element? If you buy that we can't consider a subgroup which is the identity element, so let's ask the question, well, what does it mean to say that there does not exist some h such that order of h equals to p to the theta and theta is less than alpha? Right. Does it mean that all subgroups that are not the identity have order p to the alpha? Right. If all, right? Right. Let's say you buy into this idea that assuming that our theorem, assuming that order of g to the p to the alpha does not imply this. That is that, suppose we can show that, I mean, what if we applied this strategy? We said that, look, suppose that we know that order of g equals to p to the alpha. Right? But we're trying to prove that there exists some subgroup h such that order of h equals to p to the theta. Right? Suppose we showed that having order of g equals to p to the alpha and having that the consequence is not true, that actually such a h does not exist. Suppose we showed that, showing that no h, that there does not exist a h such that h is less than, there does not exist a subgroup h of g whose order p to the theta is less than alpha. Suppose we're able to prove that, and we prove that actually, assuming that there is no subgroup of order p to the theta where theta is less than alpha, assuming that that is true, how can we put this well? So suppose we're able to show that if a h, if there is no h whose order is p to the theta, with theta having these conditions, right? Suppose we're able to show that there is no h with order of h being equal to p to the theta, and that if that were true, if if actually if actually order of h never equals to p to the theta, right? If this is true, and we're able to obtain a contradiction from this statement that order of h can't be equal to p to the theta, what would that enable us to conclude? Will we be able to conclude that actually there must exist some h whose order is p to the theta? Right. Not sure if that's making sense to you. That is, we're trying to establish that if the order of the group G is p to the alpha, that if that is true, then there must be some h subgroup of G whose order is p to the theta, right? And theta being less than alpha. Okay, that's what we're trying to establish. Suppose we proved that there is no such h, but assuming that there is no such h leads us to a contradiction, right? What would that mean? Would it mean that actually such a h must exist? Right? Contradiction. So can we use that strategy instead, right? So the question becomes, suppose that the order of G is p to the alpha, but such a h does not exist. That is, there does not exist a h such that order of h equals to p to the theta, right? What would that mean? Right? Right. Non-identity h, of course. Actually, just a h, right? If there is no h such that order of h equals to p to the theta, what does that leave us for possible values of the orders of h? If we get h subgroups of, if we get subgroups of G that are not identity, well, what possibility does that leave us? Well, is alpha minus 1 a possibility? Isn't alpha minus 1 less than alpha? How about alpha minus 2? Isn't that less than alpha? Right. So can anything less than alpha be a possible power? Right. So because if the order of every subgroup H is p raised to some power, right, some natural number, x, right, and we are saying this x cannot be less than alpha and cannot be equal to 1. Okay, what possibilities are we left with? Does that mean that, well, the order of H has to be p to the alpha? Okay, if the order of H equals to p to the alpha, can we obtain some sort of contradiction? Right? Let's see. Suppose that order of H equals to p to the alpha, all right? What does that mean? Right? If for all if for all H subgroup of G, order of H, that's non-identity, right? For all H subgroup of G and order of H not equal to the identity, if for all that, then order of H equals to p to the alpha, right? If for all non-identity H, order of H equals to p to the alpha, well, what does that tell us about G? Right. If order of H equals to p to the alpha and order of G equals to p to the alpha, right, and H is a subgroup of G, right, can we conclude that H equals to G? Okay. So are we saying that the only subgroups of G are, what are the possible subgroups of G then? Right. So if every subgroup that's not the identity has order p to the alpha, and every subgroup of order p to the alpha is just G, are we saying that the only subgroups of G are G and the identity group? Okay. Right. So if if the only subgroups of G are G itself, right? If the group is if the only subgroups of G are the trivial ones, that is the group itself and the identity group, what can we conclude? Right? Well, what can we say then? Right? For instance, what does that tell us about, let's say, the orders of elements of G? Right? Let G, little g, be an element of G such that order of G, order of little, such that, well, we could say order of little g, or we could just say that G is not the identity, right? Suppose that G is not the identity element, right? Given that the only subgroups of G are G and the identity, well, what does that tell us the order of little g has to be? What's the order of little g if if little g is not the identity? Well, can the order of little g equal to some n where n is less than the order of G? Right. Is that possible? Right. Well, suppose that for some n less than order of G was actually equal to n, right? Wouldn't wouldn't G to the 0, G to the 1, G to the 2, all the way up till G to the n minus 1, right? Wouldn't this cyclic group here, let's call it M, wouldn't this cyclic group M actually end up being a subgroup, right? Being a subgroup of G, right? If this cyclic group M generated by little g is a subgroup of G, right? But the order of M equals to n, which is less than order of G, right? Is that possible, given that the only subgroups of G are G itself and the identity, right? Well, is M the identity, right? Given that it's generated by some non-identity element, can M be the identity, right? So is M the identity? Question. If the only possible subgroups of G are the whole of G and the identity, well, we've now found another subgroup, haven't we? We found a subgroup M of G. So the question is, well, since the only subgroups of G are G and the identity, right, and M is a subgroup, then aren't we saying that M has to either be the whole thing or the identity? So let's check. Can M be the identity group? Can M be the identity group is the question. Well, how many elements are in M, right? Or better yet, the identity elements contains what element? The identity, right? But didn't we say that isn't G to the 1 an element of M? Okay, if G to the 1, otherwise known as G, is an element of M, right? Then how can G and M be the same set if G has an element, if G is in M, right? If G is in M, but G is not in the identity set or the identity group, how can M equal to the identity? Right? Is that possible? Right? Okay. If that is not possible, if M cannot equal to the identity, okay, if M cannot equal to the identity, and we are saying the only when we're saying that M is a subgroup, so and the only possibilities for M is M can be the identity or M can be the entire group. So question, if M is not the identity, right, is M the entire group? Well, let's examine that. What is the order of M? Order of M, did we say that the order of M was n? Okay. And in fact, we said specifically that the order of M is less than the order of G. If the order of M is less than the order of G, okay, how can M equal to G, right? Are we saying that M does not equal to G? Okay. So if M does not equal to G, if M is a subgroup of G, but M does not equal to G, and M does not equal to 1, how can it be true that the only subgroups of G are M, the only subgroups of G are M, or let's put it this way, if M does not equal to the identity and M does not equal to G, and we are saying that the only subgroups of G are G and the identity, right, then could this M really be a subgroup of G? Right? Is M really a subgroup of G? Right? So what did we assume about M? Because when we're creating M, we said that, well, we're assuming that there exists some element G of order n, where n is less than order of G. And with this information, we created the cyclic subgroup. And this cyclic subgroup M is what we found cannot exist because it's neither equal to the G or the identity element. Okay, well, if it's neither equal to G or the identity element, right, then can this assumption make sense? Can the order of any element ever be less than the order of the entire group? Right. Well, we're saying that that doesn't happen. Okay, so we're saying that, right, because didn't assuming that the order of an element is less than the order of the group lead us to a contradiction? Okay, if that led us to a contradiction, then are we saying that the order of G of any element can't be less than the order of G? This can't happen. If the order of every element can't be less than the order of G, okay, what are we saying really here? If the order of every element can't be less than G, but Lagrange's theorem tells us that the order of every element must divide the order of the group. What does that tell us the order of every element must be? Does it mean that the order of every element must equal to the order of the group? Okay, but what's the order of the group? Is it p to the alpha? Okay, so have we found an element of order p to the alpha? is the question, right? So again, this is very, it feels very convoluted, right? It's really a long investigation. So let's make sure we haven't lost track here. We're trying to see that, we're trying to determine if this statement is true, that if the order of a group is p to the alpha, right? Does that imply that there exists some subgroup h of g such that order of h equals to p to the alpha, equals to p, sorry? And the strategy we've come up with is, okay, well, suppose we're able to prove that there exists some subgroup h of g such that order of h equals to p to the theta, right? Where theta is less than alpha and theta is between 1 and alpha. Okay, right. Suppose we're able to find this, uh, suppose we're able to find this subgroup h of g. Would that be enough for us to prove that there exists some element of order p, right? And the argument was that if finding a subgroup of order p to the alpha guarantees us a subgroup of order less than alpha, let's say alpha minus 1, and a subgroup of order p to the alpha minus 1 guarantees us a subgroup of order alpha minus 2, and so on and so forth, then this strategy, right, this strategy seems to be telling us that indeed this strategy of always finding a subgroup of p of order p to the theta, where theta is less than the original power, this strategy seems to be guaranteeing us that we're going to have a subgroup of order p. And so the question is, how do we prove this statement then? How do we prove that if a group has order p to the alpha, then there must exist some subgroup whose power, whose order is p to the theta, and theta is less than the original power, theta is less than alpha, right? How do we prove this? And so far, this tactic we've been trying to think about is, well, we've been working by contradiction, right? That is, well, let's suppose that the order of g is actually p to the alpha, okay? Let's suppose that that's true, all right? Well, now we're picking any subgroup of g, right? Now we're saying that suppose the implication is not true. Suppose that actually no alpha, there doesn't exist a h such that order of h equals to p to the theta, right? Well, what would that mean, right? And we're saying, well, wouldn't that mean that the order of h, wouldn't that mean that for every non-identity h, for all h not equal to the identity, wouldn't that mean that for all h not equals to the identity, order of h has to equal to p to the alpha, the order of the group, right? But if order of h equals to p to the alpha, and order of g also equal to p to the alpha, aren't we saying that the order of h equals to the order of g? Okay. If the order of h equals to the order of g equals to p to the alpha, we're asking the question, well, what does that tell us about the group? Remember, we're trying to come up with a contradiction here. In particular, well, can we ever have an element of g? If we got some little g in g, can we ever have an element of g whose order is less than p to the alpha, otherwise being which is the same as being less than the order of g? Sorry. Can we ever have an element whose order is less than order of g? Okay. And we did this and we seem to be arriving at a contradiction. So if this can't happen, if the order of any element can't be less than the order of the group itself, then what are we saying? Are we saying, and given that the order of every element actually divides the order of the entire group, okay? If the order can't be less than the order of the group, and the order of every element has to divide the order of the group, can we conclude that the order of every element must equal to the order of the group? Okay. If the order of every element equals to the order of the group, right? What does that tell us? What does that tell us about our group? Okay. Well, right. What can we conclude from this fact that look, the order of every element must equal to the order of the group. All right. If this is true, then what? So what? Right. So what is the idea? Well, would that mean that then, can we conclude from there that there exists some element G in G, there exists some element of the group G such that, right, such that the order of G equals to the order of the group, P to the alpha, right? Is that true? Alright? If this is true, if there exists an element little g in G such that order of G equals to P to the alpha, alright? What can we conclude from here? Alright? So, if there's always an element of order P to the alpha, right? Well, in particular, can we think of this group here, H equals to G to the 0, G to the 1, G to the 2, all the way up till G to the P to the alpha minus 1. Let's think of that group, okay? How many elements are in this group? Is the order of H equals to the order of the order, is the order of H equal to P to the alpha? If the order of H equals to P to the alpha, and P to the alpha equals to the order of the group, aren't we saying that H equals to G? Okay. If H equals to G, well, aren't we saying then that this group G is cyclic, that actually G equals to G to the 0, G to the 1, G to the 2, all the way up till G to the P to the alpha minus 1, alright? If this is true, if G is actually equal to, if G is actually cyclic now, if we're saying that G is cyclic, are we guaranteed an element of order, are we guaranteed an element of order P? Right, is the question. Right. If we look at this group here, can we, I mean, first question, is it easy for us to construct a contradiction? Well, how can we construct a contradiction from here? Perhaps it's not so clear. Well, if it's not so clear, what can we do? Can we at least figure out if there's an element of order P? Right? Because we said that, didn't we say that if we can find an element of order P, then we can also find a subgroup of order P, right? So, can we find an element of order P? And so the question becomes, let's consider the element G to the P, right? Well, G to the P, well, first of all, is G to the P an element of the group G? Right? That's the first question. G raised to the power P, is it an element of the group G? How would we check that? Actually, do we even need to check that, right? Because what's the nature of a cyclic group? That, is it that after we get to P to the alpha minus 1, doesn't the cyclic group loop over? For instance, if we look at the group G to the 0, G to the 1, G to the 2, let's say, right? Well, we can ask, well, what about G to the 5? Is G to the 5 in this group? Well, would notice that G to the 5 is the same as, isn't that the same as G to the 2 times G to the 3? Okay. Well, what's G to the 2? Well, we know what G to the 2 is, but over here, aren't we saying that if we have a group G to the 0, G to the 1, G to the 2, aren't we saying that G to... Alright, so we just run out of time, and so last time we stopped at this point as well, but we stopped at this point after having worked, we came to this point here where we talked about, well, we were considering the element G to the P again, but we've done it using a different approach, because here we've come from the fact that, well, there is no element whose order equals to P to the theta, and from this idea we've come to the conclusion that, well, G has to be cyclic, and if G is cyclic, then we're trying to look at the element G to the P element of G, and first we're trying to consider if G to the P is actually an element of G. And if that is true, think about, well, what's the order of G to the P, right? And before we'd used a different strategy. We'd said that either we have some G in G such that order of G equals to P to the alpha, or we don't. And we said, well, if we had an element whose order of G equals to P to the alpha, then we're saying that that means that the group G is cyclic and is generated by the element G. Right? So we came back to this set again. right? If there's an element of order p to the alpha, then we said that g has to be cyclic, and g has to look like this: g to the 0, g to the 1, up till g to the p to the alpha minus 1. And then from there, again, we'd consider the element g to the p and asked ourselves, well, what's the order of g to the p? Right? That's where we'd reached before. And now we've reached at the same kind of question again in two different ways. And so the question is, given all that we've done now, can you complete the proof? Right? Can you complete the proof, or can you decide whether it is indeed true that if H is a subgroup of G and order of H, sorry, no. If order of H equals to P to the alpha, does that imply that there exists some subgroup H of G such that the order of H equals to P? Right? Can you decide whether this is true or not, given the investigations that we've done? Right. So, thank you very much for watching this, and have a relentless week. Bye.